Welcome to Math with Malia. Today we're going to work on the Savvas enVision Algebra 1, Topic 10, Lesson 3, Analyzing Functions Graphically. So the previous two lessons we looked at two new functions, the square root function and the cube root function. And this lesson will help us go through ways to determine which function a graph is representing. So here's the model and discuss, and we have a table of 5 different functions. And we can plot these points using our graphing calculator, inputting the data into list 1 and list 2. We can also just analyze the data to get the general shape of the graph by looking at the outputs and any patterns we might notice. So for f of x, the first table, what do we notice as x is increasing from -2 to +2, what is happening to the output? We can see that it is increasing by 3, and then increasing by 1, and then decreasing by 1, and then decreasing by 3. That seems to be a symmetrical pattern where it does change the direction. It goes from increasing to decreasing. And we can see that that change happens right there at 0,5. So this is likely going to be a parabola. Okay, it does not have a common first difference. Let's check the second difference. I'm going to write over the next function table, but that's okay. So going from a change of 3 to a change of 2 is actually a change of -2 for a second difference. And the next second difference is also a change of -2, and the last 2 points is also a change of -2 for the second difference. So we know from previous lessons that if we have a constant second difference, that is quadratic. That will make the shape of a parabola. And we can see that right here at 0,5, we would have a vertex where the graph changes direction. All right, let me erase some of this so we can look at g of x. As the input increases from -2 to +2, what is happening to the output? Well, going from 20 to +10 is dividing by 2 or multiplying by 1/2. Going from 10 to 5 is also multiplying by 1/2. Going from 5 to 2.5 is dividing by 2 or multiplying by 1/2. Going from 2.5 to 1.5 is multiplying by 1/2. So it has a constant ratio. That means that this is exponential. We are multiplying by the same number over and over again. Okay, let's look at h of x. I'm going to erase some of this again so we can see the table clearly. As x increases from -2 to +2, what is happening to the output? Well, let's look at the first difference. It is decreasing by 3, and then it is decreasing by 3, and it is decreasing by 3. Decreasing by 3. It has a common first difference, and we know from previous lessons that that means this is a linear function. Okay. And let's look at j of x, looking for the same thing. So I'm just going to eyeball j of x. I see that it is decreasing and then starts to increase again. There seems to be a turnaround point at 0,0. So I might think that it would be a parabola because there is a vertex, but let's double check and see what the relationship is between input and output. If I take the input, -2, how do I get the output? What do I do to the input? If I take -1, what do I do to the output or the input to get +1? Likewise, all the way through. What am I doing to the input to get the output? Well, we can see that all we're doing is taking the absolute value of the input. So absolute value would also have a vertex and will change direction. So it's important to also check the relationship between the input and the output. And k of x, let's take a look at this function. We are decreasing by 10, we are decreasing by 6, then we are decreasing by 2, and then we go up and increase by 2. So we do have a change of direction at 1,3. So likely there is a vertex, or likely it will be a parabola. It doesn't seem that it's absolute value, which is the only other function that has a vertex. So we can say that this would give us the shape of a parabola as well. Okay, let's take a look at example 1. Analyzing domain and range. So we have these 3 functions, and we want to describe their domains and range. So remember, domain is all the input values and the range is all the possible output values. The first graph, g of x. We have a quadratic term. Okay. If we're looking at the constant, we know that this is shifted down to, and we also have this negative out in front of the quadratic term. So it should be reflected, which it is. It's reflected over the x-axis and then moved down 2 units. It's a parabola, as it is a quadratic function. And so since it is a parabola, all the possible x values, there are arrows on the end of our graph. It continues to go on and on forever to the left and on forever to the right. So our domain is all real numbers. And remember, you can write that using bracket notation. So we could also see it sometimes written like this for domain. Okay, from negative infinity to positive infinity, and it's a curved parenthesis because we cannot include the number infinity. It would be a square bracket if we could include that value. The range, remember, is all possible output values, and since it is shifted down 2 units, instead of starting at 0, it's going to start at -2 and then be everything less than 2. So y would be less than or equal to -2. Okay, look at h of x. It is also downward facing. We can see that we have that negative outside of the first term. It is also shifted down 2 units, and this is an absolute value function. So again, the domain is all real numbers. All the possible input values go forever to the left and forever to the right. And the range is going to start at -2, and since it's reflected, it's going to be everything less than or equal to -2. For j of x, we're seeing a similar pattern. We still have that negative in front of the first term, so it is reflected over the x-axis. We still have this constant -2 shifting it down 2 units from the parent function. And it is an exponential function as we have x in the input. So the domain, again, goes on and on forever to the left, on and on forever to the right. So the domain is all real numbers. I'm going to show you another way you might see this written. If you have negative infinity and x is in between, whoops, it's not going to be equal to, because we can't be equal to infinity, positive infinity. So x will be in between negative infinity or positive infinity. So you can also see it written in that notation using inequalities. And the range is less than -2. Why is it not equal to -2? Well, remember, with exponential functions, we have what's called an asymptote. We have this line that the function approaches but never actually gets to that value. So it increasingly gets closer and closer to that value at -2, but it never actually equals -2. So the range will not include -2. That's why it's only less than -2. Okay, so that's how we can analyze domain and range. Just remember, domain is input, range is output. Explain how you can determine the ranges of h and j from the expressions that define them. Well, we kind of did this already when we were just looking at the functions. The negative sign means that it is reflected over the x-axis. It is the opposite of the parent function. Okay, so negative always means opposite. So it is reflected and thus downward facing. And we know that that -2 constant added to the output shifts the whole graph down 2 units. So we've already talked about that. We could just look at the equation to be able to determine domain and range for those expressions. Example 2. Maximum and minimum values. Which of these functions has a maximum value and or a minimum value? So remember, we have to look at the graph and see what the trends are, and a maximum is, of course, is going to be the greatest value, and the minimum will be the least value. So our first function is f of x equals 2x minus 3. We can see that this is a linear function. It should have a constant rate of change. Here's the graph of 2x minus 3. And we can see that it is a constant rate of change. So what would be the maximum and minimum? Does it ever reach an ending point in either direction? It does not. Okay, it keeps going on and on forever to the right and on forever to the left, so it does not have a maximum or minimum. Let's take a look at g of x. Okay. We have x in the exponent, so our input is in the exponent. We know this is an exponential function. It looks like it's going to be reflected downward with that negative in front of the 1/2 and shifted 4 units up with that constant added to the output. So here's the graph of g of x. Does it have a minimum or maximum? So it goes on and on forever to the right, always increasing as we move to the right, and on forever to the left, always decreasing as we move to the left of the x-axis. Does it have a minimum? Well, no, it's never going to reach a point where it stops decreasing as we move to the left. So as x decreases, it's going to continue to decrease. Is there a maximum? Well, not technically. There is an asymptote, so there is a point that it will not go above. It will not ever hit 4, but I can always add another decimal place to my value. I can have 3.9999991, 3.999999991. Okay, we can just keep adding another decimal place forever and ever. So it will never have a maximum or a minimum, even though it does have that asymptote at y equals 4. And here's h of x. It's an absolute value function. Also, it is shifted up 2 units, so we can see that here in the graph. It's our absolute value function, and it's also shifted 1 unit to the left because we have the +1 inside the parentheses, or the input has to add 1 to be able to move to the parent function. So if I start at h of x, in order to match it with the parent function, I have to add 1. That means it has to be shifted to the left 1 unit. Okay, so looking at our graph, there are arrows moving to the left and moving to the right, so it's continually increasing in both directions. Does it have a maximum value? It does not have a maximum because it's always increasing, but what about a minimum? Is there a point where it does not go below? Well, yes, at the vertex, that is its lowest point. That is its least value for the output, so that is its minimum. So if we have a vertex, we will have a maximum or a minimum, okay, depending on if it's upward facing or downward facing. Okay, remember, the maximum or minimum is talking about the y value or the output. Okay, is there a lowest y value or a maximum y value? Okay, example 2, try it. Does each function have a maximum or a minimum? And then do a rough sketch of what the function would be if it will help. Okay, so let's just take a look at the type of function it is and imagine what the graph would look like. For letter A, I have an x squared term. This is a quadratic graph. That means it will be shaped like a parabola. Okay, so it'd be shaped like a parabola. Why is it upward facing? Well, there is no negative sign in front of the quadratic term. Okay, so I know it's going to be upward facing. So that means that it will have a minimum value. How about g of x? It is a square root function, one that we learned in lesson 1. Okay, it's a square root function. So thinking of what the square root function looks like, just roughly, it's going to start at a point and then increase. Well, that didn't go too well. I'm going to take that. Okay, it's going to always be increasing. So will it have a maximum? No, it's always increasing since it's upward facing. That too is positive, but it will have a minimum value. It will have a starting value. Okay, so it will have a minimum. And h of x, let's take a look at h of x. This is a cube root function, okay? And it is shifted up 5 since we have that +5 on the outside. It is going to be looking like our cube root function. It might just be translated a little bit and it looks like it might be compressed a little bit. We're going to talk about that in the next lesson. We'll review compressions and stretches, but if I'm going to just roughly sketch a cube root function, that was not very good at all. But it has arrows on both ends of the graph, so it will always be increasing and always be decreasing. So it will not have a minimum or a maximum. Okay, so we'll have neither. All right, let's take a look at example 3. Understanding axes of symmetry. So we talked about axis of symmetries when we were doing absolute value functions and quadratic functions. Okay, that is where the vertex lies. It is the place that divides the function in half, and it makes the graph symmetrical. So looking at our table for f of x right here and the graph, we can see that there is a line that can divide the graph in half, and we can reflect over that line of symmetry and match each part of the graph up with each other. If I wanted to move this over here, it would perfectly line up. Okay, so we have symmetry on this axis of symmetry here, this blue dotted line, okay, at that x value at x equals -3. That is also where the vertex lies. Okay, the vertex is where the graph changes direction. It goes from increasing to decreasing in this case, since it is downward facing. So the vertex, remember, always lies on the axis of symmetry. For g of x, it is quadratic. Okay, it's quadratic. Here's the graph. We can see that it does have a point where it changes direction right there. And so there is a line of symmetry or axis of symmetry at that x value where x equals 2. Okay, so just think of the axis of symmetry like you can fold the paper in half and the two sides of the graph will match up. Okay, what about the square root function? So we talked in lesson 1 how the square root function does look like a sideways parabola, but it will not fit the definition of a function in that case. So that's why we can't have this bottom part of the sideways parabola. So without that other half, is there a line of symmetry for the square root function? Well, no. I can't divide it going horizontally because then it wouldn't be a function. And I can't divide it going vertically. It will not match up if I fold it along a vertical axis of symmetry. So again, the only functions that will have an axis of symmetry that we have talked about will be quadratic functions or absolute value functions, ones that have a vertex. Okay. Does each function have an axis of symmetry? Well, let's just remember, only quadratic functions and absolute value functions have axes of symmetry. So what kind of function do we have in A? The x is in the exponent. This is the input in the exponent. So this is an exponential function. Therefore, it does not have an axis of symmetry. And this is a cube root function. Now, you might think that a cube root function could be symmetrical. Oops. Try that again without the automatic straightening. But it's not. If I were to divide this with an axis of symmetry, this would just be like, oops. This would just be reflected over here. It would, try again. It would not match up with this part of the graph. So it is not an axis of symmetry. Okay, we're almost done. Let's take a look at example 4, analyzing end behaviors of the graphs. So this is new. We haven't talked about end behaviors yet. End behaviors just means what is going to happen as you moved forever and ever to the left on the x-axis and what happens as you move forever and ever onto the right of the x-axis. Okay, and we have a new notation to learn. Okay, as x, that arrow means approaches. So as x approaches positive infinity, that means as I am moving to, I'm going to zoom in and write this, to the right. Okay, as I am moving to the right, what's happening to the graph? And the next part is saying as x approaches, remember that arrow means approaches, negative infinity, what's happening? Well, negative infinity means we're moving to the left. Okay, so that's what that notation means. As the input approaches either positive or negative infinity, what is happening to the graph? All right, for our quadratic function, as x approaches positive infinity, as I move farther and farther to the right, what is happening to my graph? Well, it is decreasing. It's downward facing. So the output values will continue to decrease. So that's how we can write it. The output, f of x, will approach negative infinity. It's decreasing forever and ever. It's going to approach negative infinity. What about as we move to the left? As x approaches negative infinity, as I'm moving to the left, what is happening to my graph? It is also always going to be decreasing. So f of x will approach negative infinity. Okay. Let's take a look at the exponential function. Okay, remember, with exponential functions, there is an asymptote. This time it's at 0. Okay. So does it ever get to 0? Nope, it approaches 0. Okay. So as x approaches positive infinity, as I move to the right of my graph, what is happening? It is approaching 0. Okay, so we can say g of x approaches 0. But as we move to the left, as x approaches negative infinity, what is happening to the graph? Well, it is increasing forever and ever and ever. So the output approaches positive infinity. Since it is increasing, it is always going to get greater and greater and greater. What is the end behavior of this function? Okay, we have a cube root function. So again, as x approaches positive infinity, as I am moving to the left, what is happening? My graph is increasing. My outputs are increasing. So it is approaching positive infinity. As I'm moving to the left, as I am approaching negative infinity, what's happening to the outputs? Well, it's continuing to decrease. So it is approaching negative infinity. Okay, so just remember, end behaviors means what is happening to the output or what is happening to the graph as you move forever to the right and forever to the left. All right, compare the end behaviors of these functions. The first function, f of x, we have an exponential function. So what is happening? As x approaches positive infinity, what's happening to my output of an exponential function? Okay, it's increasing, so it's going to approach positive infinity. Okay, what about as x moves to the left, as it approaches negative infinity? This is an exponential function, okay? And it's exponential growth because my growth factor is positive. It's greater than 1. So as I move to the left, it is decreasing, but it's approaching that asymptote. So it's approaching 0. Okay, let's take a look at g of x. I'm going to write this one in blue. We have an exponential function again, but take a look at our growth factor. It is less than 1, so this means it's exponential decay. So if I were to draw a rough graph, it would look like that. It's shifted up 4, okay? Again, these are all things we've learned when we've talked about our previous functions individually in previous topics. Okay, so let's write it out. As x approaches positive infinity, as I move to the right, what is happening to our graph? It's approaching that asymptote. So g of x is approaching 0. Well, not 0, it's moving up to 4. It's approaching 4 since it's shifted up 4. As x is approaching negative infinity, as we move to the left, what is happening to our graph? It is increasing. So then our g of x would approach positive infinity as we move to the left. All right, the last one I'm going to do in red, h of x. We have a quadratic function, okay? So we know quadratics will be a parabola. It's positive. My quadratic term is positive, so it will be an upward-facing parabola. So as x is approaching positive infinity, as I move to the right, h of x is going to approach positive infinity as well. It's going to be always increasing. And as x approaches negative infinity, as I move to the left, what's happening to our graph? It's also going to be increasing. So h of x is approaching positive infinity as well. All right, we made it through Topic 10, Lesson 3. If you have any questions, leave them in the comments. If you have anything you'd like me to go over, please leave it in the comments and make sure to subscribe. Happy mathing!